please.
Good afternoon, I'm Katie Smith and I'll be presenting on gas permeation. So just a quick overview of my presentation. I'll be covering an introduction, the equation for flux, the apparatus sketch, the experimental procedure, the flow rate calibration, calculations, conclusion, some safety information, and finally my references. So to start with an introduction. So gas permeation occurs through a dense phase membrane, as can be seen in figure 1, where it's coming in and the solute O2 diffuses through the bulk gas film, through the membrane from the upper cavity to the lower cavity. And equilibrium occurs at the interface, where we see that the solute diffuses through the solid membrane, followed by the gas film. The concentration PA1 on the left is assumed to be equal to PA1I, which is the same at the interface of the polymer, and that's also true of the permeate. PA2I is equal to PA2, which is an assumption that makes the calculations simplified. The equation for flux. For gas permeation, this is the equation for flux. Na equals Pm over L times the quantity PA1 minus PA2, where Na is the flux through the membrane, Pm is the permeance, L is the membrane thickness in centimeters, and the difference between PA1 and PA2 is the partial pressure of the oxygen. This is my apparatus sketch, not nearly as fancy as Brian's, but it just shows the two tanks, oxygen and nitrogen, and the box here shows that the oxygen and the nitrogen are coming into the top, and those are being read by the analyzer, where only nitrogen is coming through the bottom, being read by the ZR2000, and both of these machines read in volts. And then both machines are hooked up to the PC with the data logger system. This third rotometer is empty, and these red circles signify the steel ball reading, which were changed for each trial from week to week. The experimental procedure, as I previously mentioned, the steel ball readings for N2 and O2 were varied for each trial, as shown in table 1. The membrane thickness was 0.006 inches for week 1 and 0.014 inches for week 2, and those were converted into centimeters for our calculations. For all trials, the gas flow to the lower chamber was 30 for the steel ball reading, and the lower cavity outlet flow was recorded by the ZR2000, while the upper cavity was recorded by the CO2-O2 analyzer, as I previously mentioned when I explained the apparatus. And the N2 and O2 flow to the upper cavity were varied for each one, as outlined in table 1. So continuing with the procedure, the O2 reading from the analyzer is only approximate, therefore we calculated the actual value based on the measured gas flow rates. The data logger reported the data in volts from the ZR2000 and from the O2 CO2 analyzer, and the corresponding parts per million O2 were hand reported from the ZR2000 at various points. That's shown in figures 2 and 3 to correspond to the voltage reading so that we can have a parts per million corresponding. And I will show that on the next slide. The rotometers are calibrated at 0 psig and 70 degrees Fahrenheit for air. So we needed to correct our flow rates, being that we're working with O2 and N2, and that's also shown in the calibration. And linear interpolation was used to convert these values from the scale reading to a volumetric flow rates in milliliters per minute, which I'll show in the next slides. So this is the calibration equation that we use to make our flow rate corrections. Q actual is equal to the square root, and we also, the P and T standard, as I previously mentioned, 0 psig and 70 degrees Fahrenheit times the Q calibrated, where the Q actual is the corrected volumetric flow rate in milliliters per minute. And the molecular weight is the MW. So as I previously mentioned, this is just showing the calibration where we have parts per million O2 versus the voltage, and these parts per million was what I hand recorded during each trial to correspond with the voltage reading given by the data logger on the y-axis, on the x-axis, excuse me. And you can see the equation here. I fit that equation and use that to convert all of our values. This is just, again, showing my handwritten parts per million of O2 versus the time, and then the volts on the other side, just to see how they kind of closely correlate. This is the actual output from our first run from week 1, where we had a steel ball reading of 80 for N2 and steel ball reading of 10 for O2. And we can see the upper chamber reading and the lower chamber reading time versus the parts per million from my calibration. And we can see that towards the end of the trial, both flatline or come to equilibrium. And we have graphs like this from each trial for each run, but I just put one sample one in my presentation. So for the calculations, evaluating that previous figure, we see that equilibrium was likely achieved since the O2 concentration had flatlined, and this was the value that we used in our calculations. So the O2 that permeated through the membrane in moles per time was first found, and then this value was divided by the area of the membrane using the membrane thickness. And then from there, the fraction of O2 in the lower cavity was obtained from the equilibrium concentration given by the data logger. And then the parts per million was divided by 1 million to obtain the fraction Yi for the oxygen. As I stated, the data from the logger was converted from volts to parts per million for both the upper and the lower chambers to find the partial pressure given in that figure 3. And the O2 fraction was multiplied by the total pressure to find the partial pressure. In this case, the total pressure was atmospheric. And then I have 3 tables on the following slide. The first table just shows the percent O2 flow in the upper cavity calculated based on the measured flow of O2 and N2, and that's given in table 2 on the next slide. Also, the micromoles per hour of O2 that permeated through the membrane was calculated. And finally, the PM and PM over L, which is the permeance for O2, was also calculated, and that's given in table 4. So this is just showing our data for all of our runs based on the different flow rates of O2 and N2 in table 2 for the upper cavity. We have the total flow, the mole fractions of O2 and N2, and then the percent O2 in the upper cavity. And table 3 shows the O2 that permeated through the membrane in micromoles per hour. And then table 4 uses that very first equation 1 to calculate the permeance and the PM here. And this is what we have literature values for. And so the L, the length of the membrane, or the membrane thickness, was converted to centimeters, as I previously stated. And so our conclusion, during week 2, we had problems with the N2 tank running low, and we had problems keeping the steel ball up. It kept dropping, but we still obtained some pretty good results from that week as well. The literature value given for the O2 permeation from the manufacturer of the membrane is given as 50 times 10 to the -9th barriers, or barriers is centimeters times centimeters cubed divided by seconds times centimeters squared times centimeters of mercury. Again, we had technical difficulties experienced during week 2, so that may be why some of our values are a little off. But overall, we said that we can assume that the manufacturer of this silicone membrane is correct in their reported value for their O2 permeance through the membrane. I'd just like to continue with some safety about compressed gas, and when we're working with compressed gas cylinders. Mishandled cylinders can be very dangerous. They can release potentially hazardous material, or they can become a flying projectile. whenever you're using a cylinder, make sure to visually inspect the cylinder. If it's leaking, or if you don't know what the contents are, or if it looks potentially dangerous, notify your instructor right away and don't open the valve. Use the proper protective equipment when working with the cylinder, such as goggles, and depending on what's contained in the cylinder, possibly a lab coat, and have your hair tied back, ladies, for longer hair. And always have the MSDS, or the material safety data sheet, available for the gases that you're working with, and be familiar with the health, flammability, and reactivity hazards of those gases. When working with gas cylinders, never attempt to move a cylinder by rolling it, never carry a cylinder by the valve, never leave an open cylinder unattended, never leave a cylinder unsecured, never force improper attachments on the wrong cylinder, never refill a cylinder or attempt to mix gases within a cylinder, and never discard pressurized cylinder in the regular wastebasket. Always notify your instructor or ask your instructor where to properly dispose of the cylinder once it's used. This information was obtained from the University of Milwaukee, from their health and safety website. And these are my references. Again, the safety came from the University of Wisconsin-Milwaukee.